All right, Algebra 2, we're going to start chapter 8. We're going to jump straight to rational functions and their graphs. Okay, they're going to look like something you haven't seen before, but before doing anything with it. So rational function just means that we are dealing with a fraction. Okay, so the bottom line is when we start looking at these graphs, they're going to look different, but I'm going to ask you some specific ideas about the domain. Okay, remember the domain is only restricted, right? Because I can put anything in the top, but when the bottom, whatever the function is on the bottom, q of x they use for that, when it equals 0, so that means we have a problem, right? So there's a domain restriction. And then we have two things that it can be, right? That can be a vertical line that goes through the graph, and it's called an asymptote. The other thing we can have is maybe it's just a problem with that one point, so we actually pull it out as a whole, and that's what we're going to take a look at here. All right, so here are three different functions, right? So you got first one here, and then second one, third one. So first thing you want to notice is all I really want you to do is solve the denominator for 0. So if I have x squared plus 1 equals 0, right, we're going to subtract the 1, x squared equals negative 1. We're going to take the square root of that. Well, that's plus or minus I, right? So is that a real number restriction? No, it's not. Okay, so first thing we'll say is that there's no break in this graph. So it is called continuous. It is called continuous. And the second one, it's already factored out, but what I want you to notice is we have a situation where I can divide these out. Okay, so I have a domain restriction, x plus 2 equals 0 at x equals negative 2, right? So the domain x cannot be negative 2. Since it divides out of the problem, it's kind of like having a donut, right? And that's the middle. That's the part we can take out. So this is called a hole. So there's going to be a hole in this graph, even though it's not a circle. I like donuts, especially with sprinkles. So you can put some sprinkles on there if you want to. And then the last one, we have x minus 2 equals 0, x equals positive 2 when we add 2. Okay, so x for the domain can't be 2, but this is going to be called a vertical asymptote. So we use a VA, vertical asymptote at x equals 2. So let's take a look at the graph. I have those over in the Desmos. So this was the first one, right? We found it was continuous. Look at this thing. Left to right, it just goes on and on and on. There's no stopping this thing, right? I can zoom out and you just see it continues to go. And you're like, well, I don't really know what any of these look like, so I don't know what you mean. All right, so here's our second one. And this one looks perfectly fine. So I added in the table. So notice what happens at negative 2. Right? Normally I can click on it and I can do something with it. But on the table over here, negative 2 is undefined. Well, why is that? Because that would make the denominator 0. Okay, but the graph looks like, guess what? X plus 3, the leftover portion. Okay, so we're going to be able to use a graphing technology, so it's not a big deal. But identifying the fact that it's a hole instead of um, an actual asymptote, that's going to be a big deal. All right, so here comes the last one. Whoa, look at that. This one looks very, very different. Okay, so this is the one where we said we had a vertical asymptote at x equals 2. So here it is, that vertical line. Okay, so we're going to have some bending branches here, and they're always going to be diagonal of each other at this point for us. And you find 2 is undefined. So those have those branches happening. Okay, so that's kind of what this lesson is about. We're just going to take a look at what's happening with it. Okay, so continuous graph. Okay, so that means there are no jumps, breaks, or holes, right? So that was the very first one. And that's because there are no x values and there's no domain restrictions here, no real number ones. Okay, and the second one, we ended up with a hole in the graph, right? So it was considered discontinuous. Okay, now if it's discontinuous, we say, is it non-removable or is it removable? And since we could divide it out, it is considered removable. So this is very vocab related. Okay, so if you can take it out, right, removable, but it is a domain restriction. Now in the third one we had, this is the one that had a VA, vertical asymptote at x equals 2, because we could not take it out, so it just had to stand for something else. Right, so those are the three things we're focused on today. Okay, so we're going to find if there's any points where it's discontinuous. Notice in this one, it's not factored yet. So I'm just going to set it equal to 0, x and x. Are there factors of 3 that add up to 4? Sure are. 3 and 1. So x equals 3 and 1. All right, now don't get fooled here. I had x minus 3, and up top I had x plus 3. So they don't, they don't get taken out in any way, shape, or form. So that's no big deal. Okay, so these are my domain restrictions. Okay, so domain is x cannot be 3, or 1. Now what happens there? I can't remove them, right? They're non-removable. So that makes them vertical asymptotes at x equals 3 and 1. And what are the x and y intercepts? Okay, so x and y intercepts aren't too bad. Okay, so remember I want an x-intercept is when y equals 0. That means we're going to take this equation that we had right over here. So I'm going to focus just like this. I'm going to put this over 1. So notice what happens. I cross multiply. So x-intercept, y is 0. That means I'm solving the top. So I find out that x equals -3 gives me my x-intercept. The y-intercept is when x equals 0. So that means I go back to this equation, and I'm just going to use this red highlighter. I'm going to get rid of anything that would have x. Okay. So what I have left is x is 0, and I have 3 over 3, which is 1. Okay, so I have a y-intercept at 0, 1. I have an x-intercept at 3, 0, and I have domain restrictions at 1, 3, and I will find a vertical asymptote at those points. Okay, so we're going to use some very basic ideas. X and y-intercepts, that's stuff that we did in like pre-algebra to get the idea of what's going on with these functions. All right, let's do that 3 more times here. It's a little bit of practice. If you feel like you have it, then go ahead and pause it. All right, we're going to factor this one, x plus 4 and x minus 4. So I have the domain as x cannot be plus or minus 4. All right, look at the numerator and there's nothing going on, right? Absolutely nothing. So that means that these are both going to be vertical asymptotes because I cannot reduce them. So that means positive negative 4. X-intercept, we're going to cross multiply. Right, so again, I'm going to go like this and put it over 1. So y is 0. So I cross multiply and I have 1 equals 0. Well, that's not true. Okay, so I don't have an x-intercept. So x-intercept does not exist. And what about a y-intercept? A y-intercept, remember that's where we take out all the x's. So I have x turns out to be 0. And we end up with negative 1/16. All right, so that's our first one. In the second one, okay, first thing we'll do is solve this denominator. That's always the first step. X squared equals -3, take the square root. Well, that's I root 3 plus or minus. Well, that means we don't have any domain restrictions. And if I don't have a domain restriction, I don't have to identify it as a vertical asymptote or a hole. So the last thing I would do is try and find any x or y intercepts. Okay, so if I plug in 0, right, I'm trying to find a y-intercept. All right, so going a little bit backwards this time, that means I get rid of those. I have -1/3. Okay, this is all digital, so I can put that right back. And now I think I'll put a setting equal to 0. Okay, make that over 1. So now I'm just going to solve the top. Well, that's x squared minus 1 equals 0. So I know adding 1 or factoring, right, I can do x plus 1, x minus 1. So I'm going to get plus or minus 1. And those are the only pieces of information I can have for letter B. All right, on to the last one. I'd be willing to bet this one has a common factor. So first thing is solve that bottom, x plus 2 and x plus 1. There it is. Okay, so domain restrictions, x, you are not allowed to be -2 or -1. But the -1 cancels out. So I have a vertical asymptote at x equals -2. I have a hole when x equals -1. Let's go with plug in 0 in for x. So again, we can get rid of all of these. So I end up with 1/2. And we'll start over here and get rid of that red highlighter again. Equals 0 over 1, right? That means y is 0. So we're going to cross those out. I'm going to get x plus 1 equals 0. X plus 1 equals 0. Subtract 1. That's it. -1. All right. So now I have a little bit of a problem because it says that I have a hole at -1, but I also have an x-intercept at -1. So that means we have to get rid of this one, and all the information that's valid for this one is listed above it. Okay, so we always have to double check x and y intercepts, mostly just x-intercepts. as we go from there. All right, so that's doing all of the work, but I'll have some specific questions saying, just tell me about finding vertical asymptotes. Okay, well, vertical asymptote is when I solve the denominator, x equals 2 and 3, it does not cancel because I don't see any of the similar factors. So these are my VAs. Pretty easy, right? That's a lot easier than asking you for all of the information. All right, so those are VAs. HA, horizontal asymptote. Okay, now this one is going to be pretty easy, but you have to just memorize a couple of things, okay? Now, some of you know that I like baseball. So the first one, we're going to talk about the degree. Remember, the degree is the power. So I have the first power over the first power. So in baseball, we say tie goes to the runner, right? There's a second part to the idea, right? When the ball and the runner hit the base at the same time, they say tie. Well, that's not really true. The runner has to beat the throw anymore with the replay and everything. Anyway, tangent, sorry about that. All right, so here's what we're dealing with is if they're the same, then you go on to something else, and that's going to be the coefficient. And we're talking about horizontal line, hoi, okay, ha, hoi. Okay, so that means it's 2 over 1, which becomes y equals 2. So my HA, my ha, is when y equals 2. And I need this y in here so I know if I'm talking about a horizontal line versus a vertical line as we shorten things up. All right, so that's the first thing. If there's a tie, use the coefficient. Second thing, if the bottom wins, which is, I'm not going to lie, it's pretty normal. The bottom wins, it's automatically y equals 0, right? This is the HA. All right, and if we have the degree on the top win, then there is no horizontal asymptote. Okay, as we work on this in pre-calc, we'll talk about slant asymptote and how to get that. But this is still just algebra 2, so we're just trying to get you an idea of when we use those coefficients, when it's always going to be y equals 0, right? If the bottom wins, and if the top wins, there is no horizontal asymptote. So let's take a look at these real quick. So I'm focused on these, and they're exactly the same. So my ha, that looks like AA, HA, y equals, so get in the habit right, y equals, this is negative 2 over 1, so just negative 2. In letter B, my HA, y equals, I have power of 1 over the power of 2, the bottom wins, so it's 0. And the last one, the HA does not exist. How do I know that? The top wins. The top wins. All right, so here we dropped you right into your homework. Okay, so you can bounce back and forth to whatever you need, right? So we're going to start off with the first 4. This is where most of that work is. Okay, so that's where you want to focus your time. After that, we're just talking about vertical asymptotes and then calling it either a whole or a vertical asymptote. And after that, the horizontal. And that might be the easiest part just because we determine which numerator or denominator wins.